Welcome to the deep dive. Today, we're going far beyond Earth, staring straight into the cosmos.
But our focus isn't just on the light.
No, it's on the data. A complete deluge of data that the next generation of telescopes is about to unleash on us.
We're talking about a fundamental shift.
Right. We're looking at how we're going to handle astronomical identification in the age of, well, true big data.
This is an issue of scale that science, traditional science simply hasn't faced before. Not like this.
What kind of scale are we talking about?
Well, when you talk about instruments like the upcoming Large Synoptic Survey Telescope, the LSST, you're talking about generating petabytes of raw observational data.
Petabytes. It's a number that's hard to even conceptualize.
Exactly. And those volumes are so far beyond any humans or even a whole team of humans' collective ability to process and classify in real time.
So if we want to catch those really interesting fleeting moments.
The universe's most explosive and transient events, like certain types of supernovae or, the really rare kilonovae, we just cannot rely on manual effort anymore. It's impossible.
So automated analysis isn't just a nice little efficiency tool.
Oh, not at all. It's absolutely indispensable for modern astronomy. It's the only way forward.
So the universe is giving us this fire hose of information, and what we need is an incredibly fast, incredibly smart filter to make any sense of it.
That's the perfect analogy.
And that's our mission for this deep dive. We're going to analyze a fascinating technical study that tackles this exact problem. They used advanced AI, a specific kind of deep neural network, to compete in a challenge.
The Photometric LSST Astronomical Time Series Classification Challenge, or PLASTC for short.
PLASTC, I like it.
That's a great acronym, and that's our core source material today. The challenge itself was a real-world simulation. It was designed to prepare the whole astronomy community for what's coming with actual LSST observations.
So this isn't just a theoretical exercise.
Not in the slightest.
Yeah.
The researchers' specific goal was to find a reliable, automatic way to classify these fleeting transient objects in the sky based solely on their light curves.
And a light curve is what, exactly?
It's essentially the object's heartbeat. It's the time series data showing how an object's brightness changes over time. So they're trying to create a fully automatic system that can reliably triage all these cosmic events and, basically tell us, hey, this is the one. This is the one you need to point all your other telescopes at right now.
Before it fades away.
Before it's gone forever.
Okay. So the sources we've been diving into, they really detail the application and the rigorous evaluation of this specialized neural network on just massive amounts of simulated LSST data.
That's right.
So we need to explore the specific methods they chose. I'm really interested in the architectural decisions they made for the AI.
And then we can analyze the results, the striking successes they had with certain types of stellar events.
And then, maybe the most critical part, dissect the limitations. Where did it fail? Because those failures tell us what still needs to be done when using AI for these, high-stakes, real-time astronomical identifications.
Okay, let's unpack this study. I think it makes sense to start by defining just how much of a logistical nightmare manual classification used to be. It really sets the stage.
The before picture.
Exactly. Then we'll move into the really intricate decisions they had to make just to prepare the data. There are always these necessary trade-offs when you're cleaning complex, messy time series information.
And only then, after all that setup, can we properly assess the performance.
And, crucially, the failures, especially when the network has to classify these objects on a very, very tight timeline.
Let's do it.
Yeah,
So let's
yeah.
start with that necessity, this shift to automation. If you imagine astronomy before the big data revolution, the process of classifying every single transient event, it just sounds like a truly impossible task today.
Oh, it was exhausting. It was resource intensive, and frankly, it was prone to a lot of human subjectivity.
So if we rewind the clock, what did that process actually look like?
Okay, so back in the era before these massive survey telescopes, the whole classification process relied heavily on expert judgment and, older common statistical methods. The favorite was typically something called template fitting.
Template fitting. You're basically matching patterns.
You're doing exactly that. You compare a new light curve, this new signal you've just seen, to a big library of known, well-understood light curves. You see which one it fits best.
Sounds reasonable. What's the problem with that?
The problem is simple. Scale. Template fitting just does not scale to the immense volume of data we are getting today. Not even close.
And I'm guessing it's not great with surprises.
That's the other part. It doesn't handle novel or, non-standard events very well at all. If you discover something truly new, You have no template for it. So what do?
I can imagine the sheer volume of false positives alone must have been just paralyzing.
Precisely. The process was incredibly resource-intensive. Let's walk through it. First, you'd have groups of experts, actual astronomers, whose job was to manually eliminate the obvious junk.
The noise.
The junk data, known artifacts in the telescope, things that are obviously false positives, just that initial screening step, trying to filter out the noise, could take several days by itself.
Several days just for the first pass.
Yes. Now, imagine you're left with the genuine candidates. For any high-stakes events, the ones you really care about, each of those remaining cases required a review by at least 3 experts.
3 separate experts for one object. In an academic environment, I mean, that is an unbelievable drain on resources. Why was that redundancy so mandatory?
Because of definition disagreements and the inherent subjectivity of human interpretation.
So even the experts didn't always agree.
Of course not. Even the most seasoned astronomers might lack a single, unified, objective definition for every single observed case. Or, they might simply interpret the data curves differently based on their own specialty. One person sees a supernova, another sees a tidal disruption event.
And that subjective element, that disagreement, that must slow down the follow-up observations dramatically.
It grinds things to a halt. And this is exactly why we need automation to solve the throughput problem. What you need is a reliable, objective system that can repeatedly and consistently select only the most important candidates.
The top priority objects.
The ones that will then be manually reviewed for confirmation, but at a later stage. It's about triage.
So the goal isn't necessarily to replace the human, not yet anyway.
Not at all.
It's to build a scalable, objective triage system that saves immense amounts of expert time and resources. It lets the human astronomers focus on the truly unique or the highest priority events.
That's the mission.
Yeah.
And that brings us directly to the framework that the LSST themselves established, the BLAST-C challenge.
Right. The photometric LST Astronomical Time Series Classification Challenge. That was the arena for this research.
It was, and it was designed to simulate exactly what observations from the LSST telescope will look like.
Yeah.
It was a way of forcing researchers to prepare for the reality of the data to come.
And the key question it posed was,
how well can we accurately and efficiently classify these celestial objects that vary in brightness using only simulated LSST time series data?
and the key word there is photometric data, right?
It's a critical distinction. The challenge here is the reliance on photometric data, which is brightness measured through different color filters, rather than spectroscopic data.
Which gives you much more detail.
Way more detail. Spectroscopy gives you the chemical composition, the velocity. It's the gold standard. But it's much harder and much slower to obtain. For a survey like LST, you're getting photometry for millions of objects every night. You can only get spectroscopy for a tiny fraction of those.
So you have to make your first, most important decision based on the less detailed data.
You have to. And the data the researchers used in this particular study, the raw fuel for their AI was these light curves. So we really need to understand what that raw data looks like in a table, because those are the precise features the network has to learn to correlate and interpret.
Okay, so the AI doesn't see a curve. It sees columns of numbers.
Absolutely. The light curve data essentially tells a numerical story of an object's luminosity over time, but it's much more complex than just a list of brightness points. The input consists of 5 fundamental features, 5 columns, for every single observation point.
Let's run through those 5 features. I think it's important to understand the complexity they introduce for the AI.
Okay, so the first 2 are the most fundamental. You have the flux measurement and its corresponding measurement error.
Flux is just brightness.
Exactly. But the error term is critical. It tells the AI how noisy or how reliable that specific measurement is. That's crucial for distinguishing a real cosmic event from just a random fluctuation in the measurement.
That's a really important distinction. The network isn't just looking at the measurement itself, but its own confidence in that measurement.
Okay, what about the time element?
That's the third feature, the time of the measurement. It's recorded in something called modified Julian date, or MJD. This is the precise temporal stamp for that observation.
But I'm guessing it's not like a clean lab experiment where you get a measurement every second.
Not even close. These observations are highly irregular. You might get 10 measurements in 1 week and then absolutely none for 3 months because the telescope was scheduled to look somewhere else, or there was bad weather, or the moon was too bright. The network has to learn how to interpret these irregular, unpredictable time gaps.
And the fourth feature introduces the color, the spectral dimension.
Correct. That's the filter used. Telescopes use different filters to observe the sky, allowing only specific wavelengths of light through. Here, it's the Ugrizi-Y spectrum, which is represented numerically from 0 to 5.
So the light from a supernova will look radically different depending on which filter you're using. Radically different. The network has to learn that a sudden rise in brightness in, say, the G filter, followed by a change in the R filter, means something very specific, whereas a change across all filters simultaneously might mean something else entirely. It's a complex color and time puzzle.
And then finally, this Boolean detection variable.
This is the fifth feature. It's just a 0 or a 1, indicating detection or non-detection. This is a subtle but really important piece of context. It allows the network to distinguish between a point where they looked and genuinely couldn't detect any light from the source versus a point where the source simply wasn't observed at all.
So it's the difference between we looked and saw nothing and we didn't look.
Precisely. And those 5 features, flux, error, MJD, filter, and detection, that's it. That's the entire complex basis upon which the AI must classify the entire history of an object.
Okay, so we've established the complexity of the data. It's a time series, it's irregularly sampled, and it's multidimensional with all those filters. So moving to the AI architecture, we know a standard, feed-forward neural network just won't cut it.
Not a chance.
You need something that understands sequence, which brings us to LSTMs.
Absolutely. Recurrent neural networks, or RNNs, are the general class of networks designed for sequence data. But the researchers here, they specifically chose a long short-term memory network, the LSTM.
LSTMs are fascinating. They were specifically designed to overcome the memory limitations of traditional RNNs, right? What is the key architectural difference that makes them so much better for this kind of irregular astronomical time series data?
The difference really comes down to how they manage the persistence of information over long and often unknown intervals of time.
Which is exactly the problem we have here.
It's the core of the problem. Standard RNNs have a relatively simple loop structure, but they suffer from what we call the vanishing gradient problem over long sequences.
Meaning they forget things.
Essentially, yes. They struggle to connect a piece of information from a long time ago to something that's happening right now in the sequence. The signal gets weaker and weaker as it propagates through time.
Which is a huge problem when a light curve for a long event like a superluminous supernova might span years with these completely unpredictable gaps in observations.
Exactly. And that's why the LSTM is so critical here. LSTMs were developed way back in 1997, and they introduced a much more complex internal chain structure. They contain not just 1, but 4 interacting neural network layers inside them.
And these specialized memory blocks or cells.
Right. And inside those cells, you have these control mechanisms called gates. You have an input gate, a forget gate, and an output gate. And what's fascinating here is that these gates act like little traffic controllers for the information flowing through the network.
So they let the network decide what's important.
They allow the network to explicitly learn what information to keep and what information to forget through the loop. And it can do this at arbitrary intervals. This is what makes LSTMs superior for processing and predicting time series with time intervals of unknown duration. They're just ideal for these irregular astronomical measurements.
Yeah. So they have the perfect tool for sequences. But before they could even start training it, they ran straight into a classic machine learning problem.
The classic problem, data imbalance.
Right. The initial data set had 14 distinct astronomical categories.
But nature doesn't provide them equally, not even close.
Yeah.
You might have 10,000 examples of one common type of supernova and only, say, 50 examples of a really rare kilonova.
And if you just throw that at a network.
If you train a network on that highly imbalanced data, it develops a strong and very dangerous bias. It learns that the best strategy is just to guess the most common class all the time.
And it becomes functionally useless for recognizing the rare events.
The ones you're often most interested in.
Exactly. It becomes useless for high-priority discovery.
To counter this, they performed a critical step, generalization. They had to reorganize those 14 original, highly specific classes down into just 5 generalized categories. Can we elaborate on the rationale behind these new groupings? The rationale was really survival. They needed to create robust classes that the model could actually learn from without getting confused by the rarity of some events.
So let's start with the biggest group, the one every telescope survey is kind of designed to hunt for.
That would be the S-like class. It was assigned ID 00. This one combined all the major types of supernovae, SNII, SNIX, SNIA, SNIA 91BG, and the standard SNIA.
Just lump them all together.
Right. By grouping all the catastrophic stellar explosions together, they created a very large, very robust training set for what you could call a standard transient event.
But isn't there a big risk here? I mean, an SNII, a core collapse supernova, and an SNIA, a thermonuclear explosion of a white dwarf, are fundamentally different physical phenomena. By grouping them, don't they lose the ability to distinguish that critical physical difference?
They do, and that's the necessary trade-off we talked about. They had to sacrifice the ability to distinguish between those subtle physical mechanisms in order to gain the ability to reliably identify a transient at all.
So for the initial triage, just knowing it's probably a supernova is much better than not knowing anything.
It's a huge step forward. You can figure out the specifics later with follow-up observations.
Okay, that makes sense. Then we have the groupings based on speed.
Exactly. They created the FAST class with ID1. This grouped the rapid events, things like single microlenses, kilonovae, and M-dwarf flares. These are events that peak and fade very quickly.
And the opposite of that.
The long class, ID2. This captured the prolonged events that change very slowly over months or even years. Things like tidal disruption events where a star gets shredded by a black hole, and superluminous supernovae.
And the final two categories deal with predictability, predictable versus unpredictable changes in brightness.
Right. The periodic class, ID3, groups objects with predictable repeating light changes. So you have eclipsing binaries, mirror variable stars, RR Lyrae stars, things with a clear repeating pattern.
The easy ones for an LSTM, you'd think.
You would hope so. And then finally you have the catch-all non-periodic class, ID4. This was for variability that lacks any clear structure, and it primarily consisted of active galactic nuclei, or AGNs.
Which are supermassive black holes feeding erratically at the centers of galaxies.
Exactly. Just chaotic flickering.
This generalization was a massive decision. It solved the immediate training problem by creating these manageable groups, but it also introduced a new interpretive challenge, right? If the network now classifies something as S-like, you still need another step to figure out which kind of supernova it actually is.
It pushed the specificity problem down the road, absolutely. But it allowed the core task, that reliable first-pass classification, to have a chance at success.
Now, even with these 5 categories defined, the raw light curve data still wasn't ready to be fed to the network. The LSTM needs uniform input dimensions, but light curves are highly variable in length. So what came next in the pre-processing pipeline?
Right, so since the network requires every input sequence to have the exact same dimensions, they had to standardize the size. They chose a fixed dimension of 352 measurements for every single object.
Why that specific number, 352?
It was likely chosen as a high watermark. It was probably the maximum number of observations for any single object in their data subset, or at least a number large enough to capture the full evolution of even the longest transients without cutting them off.
And how do you force a short light curve to be 352 points long?
The method is called padding. If an object only had, say, 100 measurements, the remaining 252 slots in the data array were just filled with arbitrary placeholder values.
So padding gives you that structural uniformity, but it also introduces a bunch of artificial data points that the network has to learn to ignore later. What about the other inconsistencies, like time and amplitude?
2 more critical steps. First, temporal rescaling. Remember that the measurements were recorded in modified Julian date, which is just a continuous counter count. The researchers rescaled the temporal data for every single object, so that its very first measurement was set to 0 on the timescale.
That seems subtle, but that must be essential.
Oh, it is absolutely fundamental. If you didn't do this, the network would try to learn that an object discovered in 2023 is somehow different from an object discovered in 2025, when that's completely irrelevant.
It should only care about the evolution of the object itself.
Exactly. It should only care about the relative time that's elapsed since detection. Rescaling establishes a unified baseline for comparison, measuring the object's evolution from its own observed starting point.
And finally, the flux, the actual brightness values. They must have normalized that as well.
The flux normalization.
Yes.
The raw amplitude difference between a nearby, very bright supernova and a faint, distant AGN can be orders and orders of magnitude. If you just feed those raw numbers to the network, it's going to bias its learning towards the brighter objects simply because they produce bigger numerical inputs.
So it would pay more attention to the bright thing.
Exactly. So to fix this, they normalized the flux data separately for each object using what's called min-max normalization. This scales all the flux values for a single light curve to the range of 0 to 1.
That prevents the network from biasing its attention based on absolute magnitude, but Wait, they sacrifice the knowledge of absolute brightness by doing that, right? If the model can't tell if something is globally dim or globally bright, does that hurt its ability to classify things?
That's a very sharp question. And yes, they do accept that loss of absolute magnitude information. They are making a bet. They're hoping that the shape and the rate of change of the curve, combined with the color information from the filters, provide sufficient distinguishing power on its own.
So the signature is more important than the brightness.
The theory is that the signature, the shape, is more important than the absolute magnitude, which is often just an effect of how far away the object is.
Wow. That is a highly detailed, very meticulous set of steps just to condition the data. So let's finally look at the finished architecture of the network itself. You mentioned it's a bidirectional LSTM. Why the bidirectionality? What does that add?
The bidirectional component is a massive force multiplier for this kind of classification. Think about a light curve. The object's evolution before key measurement, like its peak brightness, is obviously relevant. But its evolution after that peak, how it decays, is equally, if not more, relevant for identifying its type.
So you need to look both ways in time from any given point.
Exactly. A standard LSTM only processes the sequence forward. A bidirectional network processes the sequence both forward and backward, and then it merges the results. This ensures that it gives equal weight to past and future data and can capture dependencies across the entire timeline much more effectively.
And given that they used all that padding, they had to introduce specific layers to handle that artificial data they added.
Yes, this is a perfect example of how your architecture has to reflect your pre-processing choices. Because they inserted hundreds of arbitrary placeholder values into many of the sequences, they had to implement a masking layer right at the beginning.
And its job is just to ignore things.
That's its sole job. It identifies those padded values and ensures the network completely ignores them during all subsequent calculations. Without masking, the network would treat all those blank spaces as a genuine signal, like the object was at zero brightness, which would completely destroy the integrity of the analysis.
And then there was a global max pooling layer. What was its role in all this?
The global max pooling layer serves to condense the output of the LSTM layers. The LSTM outputs a whole sequence of data, but for classification, you need a single decision. This layer essentially extracts the single maximum value observed across the whole sequence for a particular feature.
So it's looking for the most important moment.
In a way, yes. It reduces the temporal dimensions and forces the network to capture the most significant features, like the brightest normalized peak flux or the largest normalized error, regardless of exactly where it occurs in the temporal sequence. It kind of captures the gist of the curve in a very compact form.
So after all that meticulous preparation and sophisticated architecture design, the LSTMs for memory, the bidirectional nature for context, the masking for the padding, the network was finally ready for the test.
All right, now we get to the evaluation. The network was tested on a pretty robust set of nearly 20,000 objects, 19,920 to be precise, using the complete, full light curve data. They used a couple of key metrics, ROC AUC and precision recall AUC. Tell us why using both was so important.
It's crucial because they measure different things, especially when your data isn't perfectly balanced. ROC AUC, the receiver operating characteristic area under the curve, tells you how well the model separates the classes in general. It's a good overall measure of discriminative power.
But it can be misleading. It can be, especially with imbalanced classes. That's where precision recall AUC comes in. It's much more sensitive to performance in cases of class imbalance, or when you really care about the cost of false positives and false negatives in your minority classes.
So if your goal is to find those rare events with high confidence,
then precision recall AUC is arguably the more critical measure. It tells you how precise your positive predictions are.
Okay, let's start with the spectacular success stories. Which classes did this carefully constructed LSTM just master?
The models showed exceptionally strong, almost perfect performance for 2 of the 5 classes. First, the periodic class.
The repeating patterns?
Yes. This achieved an astonishing ROC AUC of 0.99.
0.99. That is virtually perfect classification ability.
It's incredible. Its precision recall AUC was also extremely high, at 0.89.
Which makes perfect sense for an LSTM, right? The whole architecture is designed to understand and remember repeating patterns, and periodicity is the cleanest, most obvious pattern you can find in the universe.
It's the network operating exactly as advertised. It demonstrates the raw power of the architecture when you give it well-defined, clean data.
And the second high performer.
The second was the S-like class. our big group of supernovae. It also achieved very, very strong results. A 0.95 ROC AUC and an even more impressive precision recall AUC of 0.98.
Wow, 0.98. So it was incredibly precise at identifying supernovae.
Extremely precise. This confirms the effectiveness of the LSTM in reliably capturing that classic rise and fall signature of a catastrophic stellar explosion, at least when the entire evolution of the light curve is visible.
So to summarize the wins, the network excelled at recognizing the cleanest signals, the repetitive ones and the distinct, rapid, high-amplitude explosive ones. So where did the wheels start to come off?
Well, the performance dropped off substantially for the other three categories, and that really indicates the limits of the current architecture and the feature set they used.
Let's go through them.
The long class, the tidal disruption events, and superluminous supernovae achieved a relatively poor ROC-AUC of only 0.68.
Which is not great.
Not great at all. The fast class was also weak. But the absolute worst performance was for the non-periodic class, which had a precision recall AUC of just 0.40.
A 0.40 score for the non-periodic objects, the AGNs. That's barely better than random chance.
It's a very poor result, especially considering the researchers had already generalized that category to try and make it easier.
So if we connect this to the bigger picture, it seems the network really struggled in that messy middle ground, objects that do change, but either too slowly, too fast, or too irregularly for the network to build a clean, confident model.
That's a perfect summary. And the confusion matrix from the study, it's figure 7a in the source material, that gives us the full diagnostic. It shows us exactly what got confused with what.
And what did it show?
It showed that while the model was pretty effective at broadly distinguishing the periodic and non-periodic objects from the other three transient types, it had poor overall classification performance, specifically for those long and fast curves. They were often confused with S-like objects, or even with each other.
Let's hone in on that failure to distinguish between the periodic and non-periodic objects, because those two classes were meant to be clean opposites. One has a pattern, one is chaos.
Right, and this was a major point of confusion for the model.
Yeah.
It struggled significantly in differentiating between the two. It would often misclassify a non-periodic object as being periodic.
What did the study hypothesize was causing this specific and kind of weird pattern of confusion?
They hypothesized that both periodic and non-periodic objects, and specifically the active galactic nuclei, the AGNs, in the non-periodic class, they exhibit similar-looking peak patterns in their time series.
So the chaos looks like a pattern sometimes.
Exactly. AGNs vary because of all these chaotic processes happening around a supermassive black hole. But that chaos can sometimes mimic a quasi-periodic signal. You can have little flare-ups that happen at semi-regular intervals.
And this tricks the network.
It completely tricks the network. It incorrectly attributes reliable periodicity to signals that are, in fact, completely non-periodic and chaotic.
That's a fascinating vulnerability. The AI sees noise that looks temporarily structured, and because it's been trained to love structure, the periodic class had a 0.99 score, it assumes structure where there is only chaos.
That's exactly it. It developed a strong bias toward identifying true periodicity, but that made it oversensitive to any superficial peak similarities it saw in the noisy non-periodic curves.
Is the error symmetrical? Did it also misclassify periodic things as non-periodic?
That's a great question, and no, it wasn't. It's also worth noting the direction of that error was very one-sided. Mid-classifying non-periodic as periodic was common, but the reverse error classifying something truly periodic as non-periodic was extremely rare.
So if it said something was periodic, you could probably trust it.
You could. The problem was convincing the network that something that looked a little bit periodic wasn't.
So far, what we're seeing is that the LSTM is a fantastic tool for classifying these known patterns if we give it the full life story of the object from beginning to end.
That's the big if.
Right. But as we discussed earlier, in real-world astronomy, you're in a race against time. If a potential kilonova is detected, astronomers need a classification immediately. They need to schedule scarce resources, like follow-up spectroscopic observations on huge telescopes, before the event fades entirely.
This is the moment where the academic exercise meets real-world utility, and the speed of that decision-making is absolutely paramount.
So the researchers recognized this, and they performed what I think is the most critical test in the whole study.
The partial light curve test. How well can the model classify an object early in its evolution, using only a fraction of the data?
How exactly did they simulate that real-time constraint? What did they do to the data?
They created new test sets that simulated classification using only the very beginning portion of the light curve. Specifically, they tested performance using data that was advanced in time by only 5, 10, and 20 days from the initial moment of detection.
So they were basically performing a surgical strike on the input data. They were chopping off all the context that's provided by the decay and the long-term evolution of the object.
Precisely. They were asking the AI, okay, you've seen this thing for 5 days. What is it?
And did the model, the same model that achieved those 0.99 and 0.98 AUCs for the clean classes, did it maintain its accuracy when most of the data was missing?
The answer is a definitive and a rather dramatic no.
It failed.
It failed badly. The results showed a significant, a rapid, and a profound degradation in performance as the temporal advance, the lack of data, increased. And here's where it gets really interesting and, frankly, a little alarming. Even with just 5 days of data advance, the network utterly failed to achieve performance that was even comparable to the complete dataset.
A staggering drop-off. So this confirms that these LSTMs, they rely heavily on the long-term context. They need to see the latter half of the curve, not just the initial rise.
They absolutely rely on that context.
Yeah.
But the specific way the network failed is the critical insight here.
Yeah.
It didn't just get confused randomly. When the network lacked temporal information, the most striking pattern they observed was that it began to misclassify most objects as S-like.
It defaulted to S-like. That seems counterintuitive to me. Why would it default to S-like, a category of dramatic explosions, and not to periodic, which was the class that classified even more perfectly?
This failure mode is a direct consequence of the underlying data distribution bias, the very thing we tried to fix with that generalization step at the beginning.
The class imbalance.
The class imbalance. Even after they grouped the 14 classes into 5, the S-like category of the supernovae still represented the dominant, most prevalent type of transient in the training distribution. There were just more of them than anything else.
So the network learned a fallback strategy.
It learned that, statistically speaking, if you don't have enough information to reliably distinguish an object based on its shape, your safest bet, your most likely guess, is the category you've seen the most examples of.
So when the network lacks that sufficient temporal information to accurately classify the object, it panics. It panics and defaults to the statistical average. It's the network basically saying, I have no idea what this is, but the training data suggests this is probably a supernova.
That is precisely what's happening. And this is a key lesson. Limited time information doesn't just reduce your accuracy. It actively amplifies the negative effects of your underlying data distribution bias. The less data you give it, the more biased the output becomes.
Which makes early classification inherently unreliable for any of the minority classes.
Completely unreliable.
Let's revisit the fast and long classes in this context. Their performance was already pretty poor on the complete curves. So how did they fare with only partial data?
They became virtually unclassifiable. Their struggles became nearly insurmountable, and it's because of their core physical characteristics. The study suggests the difficulties with the fast and long classes stem from the fact that they often have these short-duration defining peaks that might occur only at the very beginning or sometimes the very end of the total measurement period.
So if the network only sees the first 5 days of observation, it might miss that short critical peak entirely, even if the peak happened on day 6.
Correct. Take a kilonova, a classic fast event. It might peak incredibly rapidly and then fade away within just a few days. If the model is classifying based on only partial data from the very start, it often misses these critical, short-lived, defining peak moments.
And missing the peak means you're missing the defining feature.
You're missing the whole story.
Yeah.
And that immediately compounds the classification problem. Without that key feature, the network cannot classify correctly, and the inevitable outcome is that the prediction falls back into that dominant default S-like category. This is why the degradation became even more pronounced with the 10-day and 20-day advances. The network just aggressively misclassified almost everything into the S-like bucket because it lost all of its defining temporal context.
This research has really served as an incredible diagnostic tool for the astronomical community. It shows that the deep learning architecture, the LSTM, is fundamentally sound for robust, clear patterns. But the practical challenges of real-world data, the imbalance, and the intense time pressure are currently defeating it. Let's try to synthesize the core limitations that were identified by this extensive study.
We can summarize them into 4 primary limitations, the 4 big hurdles that must be addressed for LSST to be successful. First, the model achieved reliable, strong results only for the classes with the most robust and distinct temporal signatures.
That's the S-like supernovae and the periodic variables.
Right. It works great when the answer is obvious.
Second, the struggle with the rare but scientifically valuable transients.
Yes. It struggled significantly with the long and fast classes, and that's primarily because their short duration or very prolonged peaks are easily missed or misinterpreted within a large padded data sequence.
Third, the internal confusion between the different signal types.
The model confused periodic and non-periodic objects. It kept misclassifying the noisy AGNs as regular, repeating variables because of a superficial similarity in their peaks.
And finally, the limitation that impacts real-time discovery the most, the one we just discussed.
That is the fourth and I think most damaging limitation. Performance degraded substantially, catastrophically even, under partial light curve conditions. And that led to this pervasive and aggressive misclassification toward the S-like dominant class.
It's the AI's default bias just kicking in when it's faced with insufficient evidence.
That's exactly it.
Okay, so identifying these failures is the critical first step toward improvement. If you were advising the next research team that's tackling this Pilastis A problem, what are the proposed solutions outlined by the researchers for future work?
They outline three critical areas for improvement, and all of them are aimed at tackling these imbalance and temporal sensitivity issues head-on.
Let's start with fixing the bias directly. How do they propose balancing the classes more effectively?
Okay, so improving performance on those crucial minority classes, the fast, the long, the non-periodic, it requires aggressive strategies to rebalance the data set. The most straightforward approach is something called oversampling.
You just make more of the rare stuff.
You basically do. You duplicate or, even better, you generate new synthetic light curve data for the fast and long events to give the network many, many more examples to learn from. This fundamentally changes the statistical landscape that the network defaults to when it's uncertain.
But oversampling can introduce its own problems, can it? Like overfitting to the synthetic data you just created. Was there an alternative that they explored?
Yes. The other main approach is to use more sophisticated class weighting schemes during the training process. This is where you essentially tell the network that making a mistake on a rare class is much, much worse than making a mistake on a common one.
You raise the stakes for the rare events.
You tell it that misclassifying a rare kilonova is, say, 10 times worse than misclassifying a common supernova, so it should pay more attention. Now, it's worth noting, the study did mention that their initial attempt with a simple class weighting scheme didn't yield significant improvements.
So that's not a silver bullet.
It suggests that just adjusting the weights isn't enough. They probably need a deeper architectural or pre-processing change to go alongside those balancing efforts.
Okay, so the second area focuses on exploiting the defining features of those tricky classes, especially the short peaks of the fast and long events.
Right. This suggests a change in the focus pre-processing stage. Instead of feeding the network the entire 352 measurement sequence, including all the padded values and all those non-detection entries, future work could implement strategies that specifically focus only on the actual detection moments.
Using only the data points where the detection variable equals 1.
Exactly. You'd be treating the sequence more like a sparse collection of key events rather than a continuous padded stream of data.
And the hope is that this would help it see the important parts more clearly.
The hope is that this focused approach could help capture the characteristic short-lived features of the fast and long objects much more effectively, while simultaneously reducing the influence of background noise or artifacts that were introduced by that necessary padding procedure. If the LSTM only has to process the meaningful changes, it might be able to identify the fast transients before they fade away.
And then the final and probably most ambitious path forward, abandoning the LSTM entirely for something newer.
This is the third critical path, testing network structures that go beyond the standard LSTM architecture. They suggest exploring alternatives like attention mechanisms or, even more modern, transformer networks.
The same kind of architecture that powers things like ChatGPT.
The very same. LSTMs are superb at sequences, but they can still struggle with very long-range dependencies, where a key piece of information happens right at the start and another key piece happens right at the very end.
What advantage would a transformer offer in this specific astronomical context?
Well, transformer networks, because of their attention mechanism, are generally superior at weighting the importance of different parts of a sequence, regardless of their temporal placement. They can look at the whole sequence at once.
So they might be better at distinguishing those subtle differences between periodic and non-periodic patterns that the LSTM struggled with?
They might be. The goal here is to find a network that can look at the entire sequence and give maximal weight to an early, tiny defining peak, even if the surrounding 300 measurements are just noise or background flux. It's about finding a way to capture the essential characteristics more dynamically.
So after all of this, what does this entire deep dive mean for you, the listener, who wants to be well informed about the future of astronomical discovery?
I think the core takeaway here is clarity on the current state of the art. Deep learning, and specifically LSTMs, is highly effective for identifying established, robust, and repetitive temporal patterns.
The supernovae and the periodic variables.
That much is essentially a solved problem. But the leap from that kind of pattern recognition in a balanced, complete data set to the real-world utility of early classification of rare, complex transients, that is where the real work remains.
Real world challenges.
The real-world challenges like class imbalance and the absolute necessity of identification within days. These require continuous, iterative innovation in both how we prepare our data and in the fundamental AI architecture we use. This study didn't solve the problem, but it provided the most detailed map yet of exactly where the failure points are for the next generation of researchers.
We've covered a substantial amount of ground today. We moved from the sheer necessity of automated astronomy to handle this coming data deluge.
Right, the fire hose of data.
We detailed the intricate preprocessing required to turn these messy, irregular light curves into uniform 352-unit sequences for the bidirectional LSTM.
And we analyzed its near-perfect classification of the S-like and periodic sources, which was a huge success.
But we didn't shy away from the failure points. We dissected the model's inability to handle the complexity of the fast and long transient objects, and most importantly, that fatal degradation in performance when the temporal information was limited.
That lack of context. It forced the model to just default to its statistical bias, to the abundant S-like class, and that rendered any early classification of rare events completely unreliable.
And that deep dependence on class bias under severe temporal pressure is what makes the final thought that this research leaves us with so provocative.
Indeed. The fundamental problem, when you boil it all down, is that when the model lacks temporal information, it reverts to its statistical training bias, the abundance of the S-like events.
So if class imbalance is what fundamentally drives the failure of early classification, what can we do about it?
This raises a crucial and very practical question for the LSST project itself.
Yeah.
How might future telescope scheduling, the actual observation strategy of the telescope, be optimized not just to detect an event,
But to react to it.
to react, and to immediately prioritize and capture more data from the underrepresented classes, like the fast or long transients, the very moment they are suspected?
So you're turning the burden of proof from a post-processing problem that happens in a lab weeks later
To a real-time hardware and observation scheduling issue at the telescope itself. The idea is, if we can't fully fix the bias in the software after the fact, maybe we have to try and fix the bias as the data itself is being generated.